Hello students, let us start with theorem. An n by n matrix with n distinct eigenvalues is diagonalizable. An n by n matrix with n distinct eigenvalues is diagonalizable. Okay. Next topic is eigenvectors and linear transformation. The square matrix A of order n, written as A is equals to PDP inverse. It is nothing but the matrix factorization of A. The transformation x to AX is essentially the same as the very simple mapping x to dx when viewed with a proper perspective. We know that any linear transformation T from Rn to Rm, it is a matrix transformation. If A is diagonalizable, then there is a basis B for Rn. When this is happen, when A is diagonalizable. Okay. If A is diagonalizable, then there is a basis B for Rn consisting of eigenvectors of A. In this case, the B matrix of T is diagonalizable. Hence, diagonalizing A amounts to finding a diagonal matrix representation of the map x to AX. The next theorem tells about the B matrix for the matrix transformation x to AX. That theorem is diagonal matrix representation. Suppose A is equals to PDP inverse. Where D is a diagonal matrix. Diagonal n by n matrix. If B is basis for Rn formed from basis of Rn formed from columns of P, then D is the B matrix. For the transformation x to A. What is diagonal matrix representation theorem? Suppose A is equals to PDP inverse. Means what? A is a diagonalizable matrix where D is a diagonal n by n matrix. If B is a basis for Rn formed from columns of P, then D is the B matrix for the transformation. x to AX. Okay, now we will see some examples. First example is, let T from R2 to R2 be X to AX transformation where A is equals to matrix 7 2 minus 4 1. To find basis B of R2 such that the B matrix for T is a diagonal matrix. Solution. Here we have given T from R2 to R2 be a linear transformation, be a X to X transformation where A is this matrix. We have to find basis B of R2 such that B matrix for T is a diagonal matrix. Okay. Solution. First of all, we have to check whether A is diagonalizable. First step is to check whether A is diagonalizable. In previous video, we have solved one example of diagonalizable matrix. So, first step is, first of all, we have to find eigenvalues of this matrix. We find eigenvalues of A by using characteristic equation. Characteristic equation is determinant of A minus lambda I is equals to 0. Determinant of A minus lambda I is determinant of 7 minus lambda 2 minus 4 lambda minus 1. 1 minus lambda. Okay. Find out determinant of this. This is 7 minus lambda into 1 minus lambda into minus plus 8, which is equals to, this is 7 minus 7 lambda minus lambda plus lambda square plus 8. This is equals to lambda square minus 8 lambda plus 50. Now here we have to find two numbers whose sum is minus 8 and multiplication is 50. That is minus 3 and minus 5. So lambda minus 5 into lambda minus 3. If we equate it equals to 0, we will get lambda is equals to 5 and 3. So eigenvalues are eigenvalues are 5 and 3. Okay. Now we will find eigenvector corresponding to lambda is equals to 5. Therefore, A minus lambda I becomes A minus matrix
7 minus 5, 2 minus 4, 1 minus 5, 1 minus 5. This is nothing. 7 minus 5 is 2, and 1 minus 5 is minus 4. Okay. We row reduce the augmented matrix of A minus 5I into X is equals to 0. So its augmented matrix is 2, 2, minus 4, 0, 0. Okay, which is equivalent to 1, 1, 0, 0, 0, 0. Okay, this R1 here, R column 2 does not have leading one, so x2 is a free variable. So we will get matrix x1 x2 is equals to R1 implies x1 plus x2 is equals to 0. That's why x1 is equals to minus x2. So here is minus 1, and x2 is means here we have get x1 is equals to minus x2 and x2 as it is, because it is a free variable. So this is nothing but x2 into minus 1, 1. So we get, suppose this is a vector b1. Okay. Similarly, we can find, okay, I will write here, we have eigenvalues lambda is equals to 5 and 3. Now we find eigenvector corresponding to lambda is equals to 3. So lambda is equals to 3. Our A minus lambda I becomes matrix 7 minus 3, 2 minus 4, here is 7, 1 minus 3. This is nothing but 4, 2 minus 4 minus 2. We row reduce the augmented matrix of A minus 3 into I into X is equals to 0. I will directly write here that matrix. That matrix is 1, 1 by 2, 0, 0, 0. So we will get vector x1 x2 is equals to, here x2 is free variable, so keep it as it is, and R1 implies x1 plus 1 by 2 x2 is equals to 0. So here we will get 1 by 2 x2, x1 is equals to. So this is nothing but x1 into, x2 into minus 1 by 2 1. So this is vector b2. Now this vector b1 and b2 forms a matrix P. Therefore matrix P is nothing but vector b1 and b2 as are columns of P. This is minus 1, 1, minus 1 by 2, 1. This is a matrix P. Okay. Now we have to check A is diagonalizable or not. For this we will check whether AP is equals to PD. We get AP is equals to PD. Take where D is nothing but diagonal matrix. Diagonal entries are eigenvalues. Here eigenvalues are 5 and 3. So this is a diagonal matrix. Students, verify this. AP is equals to PD. So we will get AP is equals to PD means that A and D are similar matrices. A and D are similar matrices. A and D are similar matrices. Therefore, we get P inverse AP is equals to B. Okay. Therefore, we get A is diagonalizable matrix. Diagonalizable matrix. Okay. We get A is diagonalizable matrix. Here, B1 is equals to vector minus 1, 1 and B2 is equals to vector minus 1 by 2, 1. This B1 and set of B1 and B2 forms a basis for R2. Therefore, B is equals to set B1 and B2 is the required basis. Of R2 such that T is defined in terms of a diagonal matrix. Okay. To solve this type of example, first of all check given matrix A is diagonalizable or not. Okay, and columns of P matrix forms a basis for given vector space. Okay, let us see one more example. Next example, find the B matrix for the transformation x to ax when B is equals to set of B1, B2 for a given A is equals to matrix 3, 4 minus 1 minus 1. B1 is equals to matrix 2 minus 1. B2 is equals to matrix 1, 2. Solution. We have to find B matrix for the transformation x to ax when B is equals to B1, B2 for a given A is equals to matrix 3, 4 minus 1 minus 1. B1 is equals to this and B2 is equals to this. We have already given P is nothing but this is matrix B1, B2. Okay, that is P is equals to matrix 2 minus 1, 1, 2. Okay, this is matrix P. Therefore, required B matrix is P inverse AP. Required B matrix is P inverse. First of all, we will find P inverse. P inverse is nothing but 1 upon determinant of P into adjoint of P. Okay, so 1 upon determinant of P. Determinant of P is 2 minus become plus 1. So this is 5. Adjoint of A. This is a matrix of order 2. So here diagonal entries are interchanges. So 2, 2, they are same. So there is no change. And here we have to give minus sign. Minus, minus. So here is minus, and minus becomes plus. So minus 1 plus 1. This is our. So we will get here. Okay, and this is our P inverse. Okay, so keep it as it is. Therefore, take multiplication P inverse AP. P inverse is 1 upon 5, 2 minus 1, 1, 2 into A is nothing but matrix 3, 4, minus 1, minus 1. And P is nothing but 2, 1, minus 1, 2. Take multiplication of these matrices. We will get matrix 1, 5, 0, 1. We will get P inverse AP is equals to which is a required P matrix, which is a required B matrix. Okay, we will stop here. Thank you.